Hello everyone, welcome to my channel Enthusiasm. Today we're going to look at another 4 forms of integrate secant x dx. These results are more advanced as we will make use of complex numbers and hyperbolic functions. Although they seem to be totally different, their definitions are pretty much similar. Let's start with complex numbers. First of all, we'll use the famous Euler's formula e to the power of ix is equal to cosine x plus I sine x. Replace x by negative x, we get this equation. Because negative x is in quadrant 4, therefore cosine is positive and sine is negative. And then it's simplified to cosine x minus I sine x. How is it related to integrate secant x dx? Because secant x is equal to 1 over cosine x, therefore we express cosine x in terms of the exponential terms. Add up the two equations, the sine terms cancel out. Therefore, cosine x is equal to e to the power of ix plus e to the power of negative ix over 2. Now, we can put this into the integral. So, integrate secant x dx is equal to 2 times integrate 1 over e to the power of ix plus e to the power of negative ix dx. To simplify the integrand, multiply both the numerator and the denominator by e to the power of ix. Then it becomes 2 times integrate e to the power of ix over e to the power of ix whole square plus 1 dx. What technique should we use to integrate? Let's look at the denominator. It's a square term plus 1. We can use the square identity tangent square theta plus 1 is equal to secant square theta. So let e to the power of ix is equal to tangent theta. Then the denominator is simplified to a single term secant square theta. Differentiate both sides, we have e to the power of ix times I dx is equal to secant square theta d theta. Divide I to the other side, we get this. You can see that the left hand side is already in the integral, so we put everything inside. Then it's equal to 2 over I times integrate secant square theta over secant square theta d theta. Cancel out the secant square theta terms, the integrand is just 1. Also, 1 over I is equal to negative I. Then the integral becomes negative 2i times integrate d theta, which is negative 2i theta plus c. From now on, c is a constant throughout the whole video. So we're almost done. Express the answer in terms of x, we get negative 2i arctangent e to the power of ix plus c. So what about using hyperbolic functions to integrate secant x? For the other 3 results, we are going to use the hyperbolic functions to do the substitutions. You shall see the advantages very soon. Let's look at the 3 aspects of hyperbolic functions. They are the definitions, the square identities, and their derivatives. They help us integrate secant x later on. In the introduction, we have cosine x is equal to e to the power of ix plus e to the power of negative ix over 2. Take away the imaginary number I, then hyperbolic cosine x is defined as e to the power of x plus e to the power of negative x over 2. Similarly, using the Euler's formula, we have sine x is equal to the difference of the 2 exponential terms over 2. So hyperbolic sine x is defined in a similar way. It's equal to e to the power of x minus e to the power of negative x over 2. Just like the definitions of 4 other trigonometric functions, namely tangent, secant, cotangent, and cosecant, their hyperbolic versions are defined in a similar way. In this video, we only need the hyperbolic sine x, hyperbolic cosine x, hyperbolic tangent x, and hyperbolic secant x. So everything is nice. Now let's check out the square identities. For trigonometric functions, we have cosine square x plus sine square x is equal to 1, and secant square x is equal to 1 plus tangent square x. However, for hyperbolic functions, the format of these 2 identities are different. They are hyperbolic cosine square x is equal to 1 plus hyperbolic sine square x, and hyperbolic secant square x plus hyperbolic tangent square x is equal to 1. They are the exact opposite of their peers. For the derivatives, we know that differentiate sine is cosine, differentiate cosine is negative sine, and differentiate tangent is secant square. Likewise, the derivatives of hyperbolic functions are differentiate hyperbolic sine is hyperbolic cosine, differentiate hyperbolic cosine is hyperbolic sine, and differentiate hyperbolic tangent is hyperbolic secant square. If you would like to know more about the proofs of the square identities and the derivatives, let me know in the comment section. I shall make another video to give a detailed explanation. Now everything is ready. Let's go back to integrate secant x dx. Change secant x to 1 over cosine x, then multiply both the numerator and the denominator by cosine x like this. The term cosine square x can be written as 1 minus sine square x. We can compare this form with the square identity of the hyperbolic functions. Hyperbolic secant square x is equal to 1 minus hyperbolic tangent square x. Therefore, we let sine x is equal to hyperbolic tangent theta. Differentiate both sides, we get cosine x dx is equal to hyperbolic secant square theta d theta. Using the square identity above, the right-hand side is equal to 1 minus hyperbolic tangent square theta d theta. Divide this bracket term to the other side, and bear in mind that hyperbolic tangent theta is equal to sine x, then we get cosine x over 1 minus sine square x dx is equal to d theta. We can see that the left-hand side is exactly the same as the integral. Therefore, it's just simply integrate d theta, which is equal to theta plus c. Express the answer in terms of x, we get inverse hyperbolic tangent of sine x plus c. You can see how powerful it is to use hyperbolic functions. Compare them with the trigonometric substitutions. Each type of integral has only one kind of substitution. Say, for integrate square root of a squared minus x squared dx, we let x equals to a sine theta, but no other choices. However, there's a lot of freedom for hyperbolic functions. We can use other substitutions to tackle the same integral. It turns out that we can get two results from a single substitution. Let's look at the square identities again. Secant square x is equal to 1 plus tangent square x, and hyperbolic cosine square x is equal to 1 plus hyperbolic sine square x. Compare the left-hand side, we let secant x is equal to hyperbolic cosine t. From the right-hand side of the identities, we have tangent x is equal to hyperbolic sine t. Differentiate both sides, it becomes secant square x dx is equal to hyperbolic cosine t dt. Because the original integrand is secant x to the power 1 only, so we divide secant x on the left by the substitution above, that is to divide hyperbolic cosine t on the right. We do the cancellation on the right hand side, then we get secant x dx is equal to dt. Integrate both sides, it's just t plus c. Again, express t in terms of x. We have two ways to do that. Either inverse hyperbolic cosine of secant x plus c, or inverse hyperbolic sine of tangent x plus c. It's really nice to play with hyperbolic functions, isn't it? So in total, there are 8 different answers for integrating secant x. The first 4 basic forms are discussed in the previous video. You may see that in the link above. But wait, there's one additional form of the answer. See if you can find it out in this video. If you want to know more interesting problems in calculus, please check out the videos in the playlist shown on the screen and in the descriptions below. See you in the next video.